Welcome to Ken Matrix Online Academy. Whether you're venturing into the world of complex numbers for the first time or seeking a deeper understanding, you're in the perfect place. I'm thrilled to introduce engineer Ken Wema, our guide through this captivating topic. His expertise will illuminate the intricacies. Remember to subscribe for an abundance of advanced and engineering mathematics content. Get ready to amplify your knowledge at Ken Matrix.
The topic of this tutorial is complex numbers. Under this topic, we are going to discuss the following. We are going to have a good introduction where we're going to discuss, or rather talk about the meaning of the word, of the meaning of complex numbers, history of complex numbers, and the real life applications of complex numbers. Next, we are going to see the basic of complex numbers from the Cartesian form and how it can be represented, that is imaginary and the real part. Next is we are going to look at Argand diagram, that is the representation of the complex number in an imaginary line, imaginary axis, and against the real axis plane. We are also going to talk about operations on complex numbers, that is addition, subtraction, multiplication, and division. Next is the equations involving complex numbers. We are going to see how to equate equations that have got complex numbers. Next is we are going to look at polar form over complex numbers, how complex numbers can be represented in a polar form. The last part is we are going to see a few examples on complex numbers that are related to engineering. So let us go to the introduction. What is a complex number? This is a number which has both a real part and an imaginary part. So this is a number that constitutes of two parts, the real part and an imaginary part. So I know you have come across so many types of numbers, but this is a type of a number that has got both real and imaginary part. All the numbers are real numbers, be it prime numbers, be it natural number, and so on. So let us briefly look at the early development of complex numbers. René Descartes, Greek mathematician and a philosopher, once came up with a concept of imaginary numbers, but it was not very well stipulated. Girolamo Cardano, an Italian mathematician, also tried to bring some contribution in complex numbers. Still, it did not provide a well-organized kind of a concept on complex numbers. It was not until Carl Friedrich Gauss, who was said to bring into the whole picture of complex numbers in a scientific form, or rather in a form that can be conceptualized. Now that we have looked at a brief development of complex numbers, let us go to the real life applications of complex numbers. Where do complex numbers get to find a use? We're going to start by looking at signal processing. Signal processing involves representation of signals in a frequency domain. When that is so done, an imaginary part of the signal and the real part of the signal have to be figured out. And that is how complex number comes into the picture. In alternating current circuit analysis, the concept of current and voltage where they have to be calculated to find the impedance, to find the phase angle. So in that particular context, complex numbers must be looked at. And the electrical engineers and the students doing electrical engineers can agree with me that you do a lot of complex numbers. In quantum mechanics, though in the beginning when the concept of quantum mechanics was born, complex numbers was not regarded. But as time went by, it was so important to involve the concept of complex numbers because, for example, in the Schrödinger equation, complex numbers are used. Let us look at the last application of complex numbers in real life: electromagnetism. Electromagnetism is a field. It is formed between the interrelationship between magnetic field and electric fields at right angle. Now, the electric field is normally a real field, and the magnetic field is an imaginary field. So you can now see how complex number is important. Those are just a few applications. There are so many, but so that we can be able to see how it is used, I thought it wise to focus on only those. Now let us go to the next part of this particular topic, that is Cartesian form of complex number. We are going to consider a quadratic equation in this case, and the equation is x squared plus 4x plus 9 is equal to 0. Most of the quadratic equations and maybe cubic equations have got real solutions, and we are going to see the solution of this particular quadratic equation. It comes a time when you're trying to solve this equation and then you try to use a normal calculator, not the programmable, you realize that it gives you a syntax error. So in this quadratic equation, it boils down to something that cannot be manageable, cannot be managed by a simple calculator. Now, what is that? Let me highlight. What is this? We have square root of negative 20. Now, whatever is inside this square root sign is known as a discriminant. And for the solution to be real, the discriminant must be greater than 0. If the discriminant is less than 0, in this case, the discriminant is negative 20, whatever is just inside the square root is the one we are referring to discriminant. Then, if it is less than 0, then the solutions to that problem or that quadratic equation are not real. What are they? Let us see to the next. Let us look at the next steps. Okay. Let us look at the next steps. So x is equal to negative 2 plus or minus square root of that. So let us see how it's solved. Now, the reason why I've decided to factor out -1, because you know that -1 times 20 is -20, is so that we get to know, let me use my pen here. I'm going to use which color? Let me use this. Oh no, let me use that. Now you look at that, square root of -1, and you factor out -20, it now becomes simpler in a manner that we can get the square root of 20. The square root of 20 is a real number. But what is square root of -1? The square root of -1, square root of -1 is the square root of -1 is equal to I or J. Now, what is I? I represents an imaginary number. Now, in pure mathematics, we normally use I. In engineering, because almost especially electrical and electronics engineering, there's calculation involving current, and because I is used to denote current, to avoid confusion, J is used. In this particular lecture, we are going to adopt J instead of I. Now, we can either use I or J to mean negative, square root of -1. Now let us look at what the solution gives, what the solution we have, the solution that we have. So x is equal to x is equal to -2 plus 2.236i. Why are we saying I? Because I represents square root of -1, or x is equal to -2 minus 2.236i. What is I then? Once again, it represents negative square root of -1. Okay, so let us now go to the next step. The real part is -2 and the imaginary part is 2.236. So the real part is the real number, the number that just comes before plus or minus. And the imaginary part, it is the part that is under the square root. The part that has got I or is a multiple of J or I, whichever. Now that we have said that square root of -1 is equal to either I or J, and I have said in this case we are going to use J. So J is equal to square root of -1. But also, when you say J squared is equal to -1. Why are we saying so? Why are we saying so? We are saying so because root of -1, the square root of -1 times root of -1 is equal to -1. The square root of the square root of a number, okay, the square root of a number multiplied by the square root of a number is equal to that number. We are borrowing that from science. Now, but also we can say that, we can expand it further and say that J raised to power 5 is equal to J into bracket multiplied by J raised to power 4, which is equal to J. Now what is J raised to power 4? J raised to power 4 is the same as J squared times J squared. J squared times J squared, J squared times J squared times J squared is equal to minus 1 times -1, which is equal to 1. and 1 times j is j. So you can see the relationships, the powers of j and -1. So those are the relationships that we can derive from the fact that j is equal to square root of -1. Now let us go to the next part of this tutorial, and that is adjunct diagram. What is adjunct diagram? Excuse me. This is the representation of a complex number in a Cartesian plane. It can be, now we are going to be very categorical here. We are going to call it an imaginary real number axis. Now, if we have the 3 numbers, a is equal to 2 plus j9, b is equal to -3 minus j7. Now, don't be confused or don't be worried if this j comes before the number. In this case, in complex number, especially when we are using excuse me, we are using j, the j comes just before the number, so you don't need to confuse that. So if a is that or that, a, b, and c can be represented in the adjunct diagram as shown. So let us look at the adjunct diagram. There is it. That is our adjunct diagram. So you can see that. Let me try to explain what this means. Now, if this is a, the y-axis represents the y-axis. Let me try to use my pen once again. The pen, I want to note something. This is imaginary, that is real. So the y-axis is the imaginary axis, and the x-axis is the real axis. Then now, how do we plot that? We pick the first digit, that is the real number, and the real number is the x-axis. So in a, 2 plus j9, the real number is 2. So 2. And what about the imaginary part? The imaginary part is 9. So this is the point. You connect that point with the center, and in that so doing, you have constructed or you have represented this complex number in an adjunct diagram. This is called adjunct diagram. Now to add, also for 5 minus j10, we start by writing 5. We locating 5 in the x-axis. So the x-axis is the real axis, the real number axis. So 5, okay, and then -10, and that is c, 5 minus j10. We go to b. B is -3 in the x-axis, and it is -7 in the y-axis or imaginary axis. Now, something else that we need to note is that the pictorial, or rather the diagrammatic representation of that particular of such can also give us some more insights. What are they? We can be able to get the angle that is subtended by that line. But we normally use a convention of that convention, such that the angles in that direction, in the anti-clockwise direction, in that direction, they are said to be positive, while the angle moving in that direction is said to be negative. We are going to see that later in the polar form of complex numbers. Now let us proceed further. Let us proceed further. Operations on complex numbers. We are going to start with additions. Now, if you have ever done some little bit of algebra, I know you must have come across the term collecting the like terms together. That is what you're going to do here. The terms that are bearing j shall be collected together, and the terms that are not bearing any j, or rather the real part, are going to be collected together. If we have z1 is that and z2 is that, we want to add z1 plus z2. That is what is happening, and then we collect the like terms together. So an example like a is equal to plus j4 and b is equal to negative 1 minus j7. We are just going to collect this 2 and negative 1 together. Same to this 4 and negative 7 together, as shown. A plus b is equal to 2 minus 1, like that, then get the final answer. So let us go to subtraction. What we have done in addition will also be applied in subtraction. You collect the like terms together, like that. Now if a is equal to 2 plus j4 and b is equal to negative 1 minus j7, then that can be calculated by collecting the like terms together, as shown that way, resulting to 3 plus j11. Now let us now go to multiplication. In multiplication, now I want you to think about expansion. I want you to think about expansion. I want you to think about expansion. Now, with expansion, or let me pick a red one. With expansion, we have to multiply z1 and times z2. So, in that case, you see that is the normal expansion, where there's going to be a mix-up between the multiplication of a real number and an imaginary number. Now, this can be simplified further by representing it that way. You look at that. That is the simple formula, or the simple way to evaluate, to multiply this particular number. Just identify what a is. A is for the z1, the first complex number. It is the real number, and b is the imaginary number of the imaginary part of the first number. C is the real part of the second number, and d is the imaginary part of the second number. And this, we are going to use it. And I know it has been, if you do the expansion, I encourage you to verify that. Do the expansion and see whether you're going to arrive at this. You will reach at a point whereby you will require to say j squared is equal to negative 1. Now let us look at a very simple example there. E.g., if a is equal to 2 plus j4 and b is equal to negative 1 minus j7, then we are told to get the product of a and b. Then by adopting these substitutions, okay, by adopting such substitutions, we are going to arrive at this. Now, just need to know, this is our A, this is our B, the coefficient of J. This is our C, and this is our D. 7 is our D. So after identifying such, you come and substitute in this equation. Do the substitutions in that equation, and then you'll arrive at that. Also, I encourage you to verify. Try to do the calculations. Try to substitute in that particular formula, and then you arrive. You see where you're going to arrive at 26 minus j 18. Now let us now go to the most important part in this section, and that is division. With the division, it's going to be evaluated this way. Let's say Z1 is that, Z2 is that. Then you have to divide. Obviously, you're going to take the numbers as they are and you divide according to the order or according to the way you're supposed to divide. Now, let us look at an example so that we can be able to look at something interesting. And what is it that is interesting? It is a concept that you might have learned in SATs. Try to recall conjugate SATs. Now, if that is what we ought to do, to divide this by that, we are going to get that. That is just simple expression. We are just having an expression of a division. Then we ought to divide that. We have to make sure that the denominator does not bear the j. Then here comes what I was just about to mention: conjugate complex. So the conjugate of this number of the denominator, let me go back. Allow me to go back a little bit. This is the denominator. I want to take you back to SATs. Let's say root 2 plus root 3. The conjugate of that SAT is root 2 minus root 3. What you need to do is to change the sign. Okay, now if this is negative, you just change the sign to positive, like that. So the conjugate of -1 minus j7 is -1 plus 7. So we have just changed this sign, and that is how we've gotten the conjugate of that denominator. So for us to make sure that the denominator does not bear the j, what we do, okay, the concept of j squared is -1. So that has to be noted. So to remove the denominator, this is what you do. You multiply with the conjugate side, this one here. Let me select a pen. The conjugate side, that one there. We multiply both the numerator and the denominator. Now that we have already seen how multiplication is done, you can always refer to the multiplication and see how these substitutions come in. And then still again, looking at j squared is equal to -1. This is gonna be applied here, and maybe we can remind ourselves about quadratic identities. So quadratic identities: a minus b, a plus b is equal to a squared minus b squared. That is the analogy that is being used here. And also the concept of j squared is equal to -1 also applies here. You can always try to expand that, see whether you're going to arrive to this. And the answer is -3/5 plus j 1/5. Let us now go to the next part, the complex equations. Ever heard of equations? When you talk about equations, one thing that comes in our minds is that there's something that we ought to calculate or to find. Most of the times it is x or y or whichever, or the unknown. So if equation is in this form, we just equate the real parts, okay, and we also equate the imaginary part separately. Okay, so we are going to see that x is equal to a, this x is equal to a, y is equal to b. Why is y is equal to b? Because y is bearing an imaginary part, or it's an imaginary number, and also b is an imaginary number in the other side, in the right hand side. Now let us look at an example. Here, e.g. 14 minus j18 is equal to minus 3 over 5x plus j 1 over 5y. So what you're going to do, you equate that with this y. These are real parts, and then you come and equate that 18, negative 18 with that, because they are imaginary parts. Now let us see. Minus 1 over 3x is equal to 14, so the value of x is negative 23.33. 1 over 5y is equal to negative 18, y is negative 90. Now let us go to the next part, and this is the juicy part. And what are we talking about? We are talking about polar form of a complex numbers. Now, we have seen how complex number can be represented in the Argand diagram. The next thing that we are going to expand on that. We are going to expand on that. And how are we going to do it? You remember me mentioning the angle? So we have an angle there, and we have a triangle kind of a figure, and the triangle is surrounded by a circle. From the center to this point here, that is the radius, and from this point here to that point, that is the x, and from that point to that point, that is y. So we can see that x is equal to, x component is equal to r cosine of theta. Let's say this angle is theta, and y is equal to r sine theta. Why are we saying y is equal to r sine theta? Because y is the vertical component of r, x is the horizontal component of r. Now, from your basic trigonometry, I think you can be able to picture that. Now, what are these trigonometric relationships useful? They are useful because we're going to use them in the polar representation of complex numbers. Now, let us briefly look at the derivations of this from the rectangular form, rather Cartesian form, to polar form of complex numbers. Now, if we all know that a polar form is in that nature, z is equal to x plus jy. Now, we've just seen also that x is equal to r cos theta, because r is the horizontal, x is the horizontal component. And we have also seen that y is equal to r sine theta. Now substituting the values of x here and y, this cos, the sines, the r sines and the x cos, we arrive at that. So what have we done? We have just substituted the values of x and y in the coordinate or rather the Cartesian form. Now this can also be simplified further by representing it that way. Z is equal to r, the argument is theta. Now what is theta? Now from our basic trigonometry, if this is our triangle, and then that is why, let me draw it this way. If this is the triangle, this is y, this is x, then and that is theta. Our tan theta, or theta, is tan inverse of y over x, opposite over the adjacent. So that is how we get theta. How do we get r? Okay, from the Pythagorean theorem, r is equal to square root of x squared plus y squared. That is the Pythagorean theorem. Now you can see that these concepts are related to the concepts that you already know. Pythagorean theorem, trigonometry, the Cartesian plane, and so on. Now let us look at an example. But even before we look at an example, let us define these terms. What is r? R is called modulus or magnitude. The theta, that angle, is called argument. So we are going to represent these complex numbers as modulus and as argument. Let us see. Look at one example. If z is equal to 5 minus j10 is the Cartesian form, it can be written in the form, we can write it in that form, and or in that. This is just a simple way of writing it, because this one is somehow lengthy. Now we have to get theta and we have to get r. But before we get those particular numbers, we have to identify the x and y. So what is our x? Our x is equal to 5. And what is our y? Y is equal to negative 10. So let me use a pen here. This is our x, and that is our y. Y is not, we are saying negative 10 because we are taking the coefficient of j. So that is y is negative 10, not 10, negative 10. So that is why we already identified. Now we can now use the formulas theta, those formulas that we have looked at before. Say theta is tan inverse of y over x. Okay, so and so that is theta. R is equal to the square root of x squared plus y squared. So using the formulas, you can see how they have been substituted. We have seen 5 squared plus r is equal to 5 squared, this 5 here, plus negative 10 squared, that one there, it results to 11.18. Now what is theta? Tan inverse of negative 10 over 5. So once again, the the x, this is the x substitution, and this is the y. So y over x, tan inverse of y over x, is equal to negative 63.43. Now, there's something that is coming out here. Allow me to explain something else. Assuming that is the Cartesian plane, and that is a unit circle, I'll say that in that direction, the angles are positive. In that direction, let me use a different color so that in that direction, it is negative. So if the angle, we are seeing that our angle is negative 63.43, but we need an angle that is positive. So what are you going to see? It's negative somewhere here, minus 63.43. So it falls in the second quadrant. This is the first, this is the second, this is the third, and this is the fourth. So it falls in the second quadrant. So what is the positive angle? Just say 360 minus 63.43, and you get 296.6 degrees. So it has to be presented in as a positive angle. Now, let us now see how it can be represented in a polar form. So that is the polar form. This is the r, this is the argument or theta, this is the argument or theta. It can also be represented just as simply as that, 11.18 and 296.6 degrees. Okay, let us proceed. Multiplication and division in polar form. We want to see how polar form complex numbers can be multiplied and can also be divided. So if we have z1 and then we want to multiply with z2, we are just going to use the r, the radius, r1 times r2, okay, into the bracket theta 1 plus theta 2, as simple as that. If you want to divide, say, z1 over z2, that is equal to r1 divided by r2 into the bracket theta 1 minus theta 2. Now, I want you to think about logarithms, laws of logarithms, and maybe if you can try to think about that, then it can help you understand this particular relationship. I'm not just saying that this is the same as logarithms. I just want you to try to think about it a little bit. Now, let us see z1, z2 is equal to r1, r2, then theta 1 plus theta 2. Okay. Let us look at an example. If z1 is 3, the radius, or rather the modulus is 3, and the argument is 30. z2 is equal to the modulus 5, argument 4 degrees. What you do? You multiply, you just multiply the moduli and you add the arguments. And here, this is the result. Let us go to the division. So, division, this is the division, okay. How do we divide? z1 over z2 is equal to r1 divided by r2 of theta 1 minus theta 2. Here what you're doing is that we are just dividing the moduli and subtracting the arguments. Let us look at an example, that case. If z1 is equal to 80 degrees and z2 4 degrees, we can do that by taking 20 over 5, then 80 minus 4, that is the argument, subtract the arguments, then the answer is 4 and 76 degrees. Now, I want us to look at a comprehensive example that shall apply all the concepts that we have already learned, and that is a combined operations on the complex numbers. In this question, the question reads, if Z1 is equal to 2 plus J5, Z2 is equal to 1 minus J3, and Z3 is 4 minus J, determine in both Cartesian and polar forms the value of Z1, Z2 over Z1, Z1 plus Z2 plus Z3, correct to decimal places. So we are going to do these calculations first in Cartesian form, and then after that we do the conversion later in polar form. So the Z1 is equal to that, Z2 is equal to that, and the Z3 is equal to that. So we want to simplify that expression. When we want to simplify, we just substitute the values. Now, in substituting the values, that is what we get. Now, I want to remind you once again what we have learned in multiplication. Apply that multiplication principle, okay? And then you see where they're going to arrive at that, okay? Now here we have talked about addition. Apply the addition, see whether you're going to arrive at that, plus that. Now, here comes another thing that we have just learned before, that is division. We have to identify this. This is the conjugate, the one in red, highlighted in red, conjugate. That is the conjugate of this denominator here. So it is multiplied both sides so that it is simplified, so that we make sure the denominator does not bear the j. And now it is now simplified that way. Remember, we have to combine that with the 4 minus j. After combining that, we arrive at this. So that is the complex, sorry, the Cartesian form of the complex number. But we have to convert it into polar form, because as the requirements of the questions, that has to be done. The polar form, if x is 8.08, this is 8, this is the x, and this is y, like we have seen, r is equal to that, the square root of that, x, and plus square root of y squared. You get that. How do we get the argument? Argument tan inverse of y over x. So this is our y and this is our x. You get that. So representing it in polar form, that is the answer. Alternatively, we can just say cos 8.2 into bracket cos 9.76 plus, yeah, like that. Now let us go to this second comprehensive example. Now here we are now into a practical example, that is an aircraft. An aircraft P, flying an aircraft P, okay, flying at a height, at a constant height, has a velocity of 400 plus j 300. So that is the velocity. So that is the plane P. And another plane, or another aircraft Q, at the same height. So that means they're in the same plane. So we're going to create the height as the same plane. Because they're in the same plane height, then that means they're in the same plane. So try to think it that way. The height has a velocity of 200. So the other one has got a velocity of 400 plus j 300. The other one is 200 minus j 300. Now, determine A, the velocity of P relative to Q. B, the velocity of Q relative to P. Express the answers in polar form. So, we have to ask ourselves, what is a relative speed? What is a relative speed? What is a relative speed? A relative speed is speed that relates two bodies in particular motion, two bodies in motion. So in this case, the one that has got the highest speed is P. P has got the highest speed. So the relative speed, the velocity of P in relation to Q is simply P minus Q. It's shown that way, P minus Q. And from the subtraction, we are going to see it boils down to 200 plus T900. Now, because this is a practical problem, we have to visualize. Now let us look at it when it is represented in the Argand diagram. Now, this is the resultant direction. That is as a result of, let's say, the relative speed or relative velocity. This is the velocity of P, and that is the velocity of Q. So when you combine, and how do you combine? By subtracting P minus Q. We have seen the subtraction. Now, after doing that, you realize that P minus Q is like a reflection. Assuming this is your x, y is equal to minus x axis, is a pure reflection of this P minus Q, so that this is negative. Okay, so this is P, this is Q relative to P, and this is P relative to Q. So what is that angle? We are going to see the angle. So that is the angle. Okay, then this is also the other angle. The other angle we are going to see later. The other angle, the first angle and the other angle. This is P relative to Q, and this is Q relative to P, because it is in the opposite, exact opposite. It is a reflection along the mirror line. Y is equal to minus x. Now let us now go to the solution. We have seen that. Let us go back. This 900 here is the y component. This 200 here is the x component of the resultant, or rather the relative velocity. So we are going to use them in finding the polar forms. So we just substitute 200 and 900 to get R, and the R, which is the resultant force, resultant velocity, is equal to 922 kilometers per hour. What is the argument? The argument will give us the direction of this resultant velocity, theta. This gives us the direction. And I have said, since the direction is positive, it is going to take, conventionally, it's going to take the direction, that I've already shown previously. And then this is the polar representation, but we have to identify what they are because they're practical case. P is 922 kilometers per hour at 77.7 degrees from where Q is. Okay, and because that one is the exact opposite, P, the resultant in related to each other is opposite. That is 180 minus 77. Q is 922 at at this, from this angle from P to negative 102.53. Why I say negative? 180 180 minus 77 is that. Now we are saying negative because of the direction. Remember, here we say that in the clockwise direction it is negative, in the counterclockwise direction it is positive. That is the sign convention that is used. Now let us now go to the next example, and that is the last example in this tutorial. The four coplanar forces act at a point A as shown in the figure. Determine the value and the direction of the resultant force by drawing and by calculation. We are going to use calculation. Now, these are the forces, the coplanar forces. We want to get the resultant. Now, what are the resultants? Now, let us get to identify them. Here are the forces. 4, radius 4, angle 90, argument 90, modulus 7, the argument is 315. Let me explain why it is 315. Look at that. Look at that. From that to that is 90 plus that, 90 plus 45 is equal to 135. So that is 135. So let me use another. So that you're talking about that angle there. Okay, talking about that angle there. Right from 37, sorry, the angle here. So this is the angle we are talking about in this direction. Sorry, in that direction from sorry for that. The direction of that angle that way. So the positive direction, we are talking about the positive direction. So you are going to say 360 minus 315. Sorry, minus 360 minus 135 to get 315. That's why 315 is coming in. And the first three, F3 is the modulus is 8 and the argument is 225. How are we getting 225? First 3, 8. From here to here, the angle is 180. From that point to that point, we have seen that angle there. Now from the x-axis, we are relating the x-axis. From the x-axis in that direction, the angle is 180 plus 45. 180 plus 45, 180 plus 45. That is 225. And the other one is 5180. 5180. So the angle is now just something to note here. Let me use a red one. We are relating all the angles with respect to x. So each angle will be related to respect to x-axis. But in which direction? If it is in that direction, it is positive. If it is in the other direction, the clockwise, it is negative. That is the convention that is used here. Now, after getting all those particular angles, all that information, we can now go to the computations. And these are the computations. in the rectangular form. So we convert this into the rectangular forms before we even add. Now, for F1, we have to substitute 4 in the R and substitute 90 in the as the argument. The same for here, okay? And then we arrive at J4. In the F2, we substitute 7. 7 is the modular in that case. 315 is the argument. So after doing that, you arrive at that. What about F3? You do the substitution respectively as it has been seen earlier, and then you arrive at that. So F4 that way, and then you arrive at -5. Now F1 is that they all get simplified up to that. Then now the next step is to get the coplanar forces, the resultant force of the coplanar. What's the resultant force? Is equal to F1 plus F2 plus F3 plus F4. So we are going to add this. We are going to add this plus this plus that. We're going to add F1, F2, F3, F4 like that, as shown that way. So after adding, we arrive to this. And then now, because the question has asked us to present it also in a polar form, we'll have to identify our x, that is our x, identify our y is -6.61. Then now we get the r. This is the r. The modulus is 8.735. And then we get the argument. That is, so note that the argument gives us the direction. So whenever you're asked about the direction, it is the argument you're supposed to find. So it is 8.735 newtons in 48.18 degrees. So that is the end of this particular lecture. Thank you for watching. Let us meet in the next lecture.